that we are meeting. Actually, chemical reactions started way back in grade 6, grade 7, when we were looking at photosynthesis, how plants make their own food. Few chemical reactions were discussed there. We kept learning more until we get to this point where much more of the details will be discussed. Much more of the details will be discussed. So I would say any chemical reaction that you have, a chemical reaction, a successful one for that matter, is made up of two chemical species. Any chemical reaction that you can think of, for as long as that chemical reaction is successful, and when you say successful reaction, is that reaction that led to the formation of products. So if it is successive, we expect to have two chemical species. And which ones are they? The first one are the ones that we call reactants. And the second one are the one we call produce or products. So any successful chemical reaction that you might think of, that you are likely to have two things, the reactants as well as the products. But maybe the trouble may come if a chemical reaction is given and then you are told to decide which ones are reactants and which ones are products. How would you know? Or what is it that is there to provide a clear-cut distinct between the two? We have a direction arrow. So let me just give you a general reaction where we are saying reactant A reacts with reactant B to produce product C as well as product D. So in this general equation, we have two things. Which ones are they? We have the ones that are written on the left-hand side of a chemical reaction, and the ones we are calling reactants. And the ones that are written on the right-hand side, they are the ones you're calling products. This introduction is very important because there are some few things that you have to understand. Remember, I said today's focus is not the introduction of chemical reaction, but the detailed part of it. So we have the reactants, we also have the products. Any successful chemical reaction that you have, what are the things that actually happens? Let me give an example. Before you start cooking in shima, the only thing that you have, maybe it's water, as well as mealie meal. There is no shima. And then at the end of the cooking process, you will have shima. Perhaps water and mealie meal will have been finished. So those are two concepts that I want to bring to your attention. That at the beginning of the chemical reaction, there's no product. Right at the start of a chemical reaction, there's no product. Products will only appear within the proceeding of a chemical reaction or at the end of a chemical reaction. But what about reactants? Reactants are the ones that are there at the beginning of the reaction. Certain reactions, at the end of it all, the reactants will have been done. So those are the two concepts that we are going to introduce this chemical reaction with. So let me put them up here as exam tips. Allow me to rub here. We are saying that exam tips. Tip number one, at the start, at the beginning of the chemical reaction. Number one, there is no product, or there are no products. And this point actually is very, very important, even in our day-to-day life. Let's say you are starting up business. Someone out there is doing business successful, then you also want to start a business. Right from the beginning of your start, you want to compare how well your friend is doing who started some time back and you who is starting now. So you have to understand that in business, right at the beginning of the business transaction, there's no profit. The profit will come as the business goes on, or maybe at the end of the business period. So at the beginning of a chemical reaction, you don't expect any product. Secondly, there are plenty of reactions, but it's not always that reactants should be more than one. There are certain reactions where we only have one reactant. And this type of reactions are the ones we call decomposition reactions, because the decomposition reactions actually start with one, and then at the end of the day, that very one that you have gets to disintegrate. You get to have more than one product. So it's not always that at the beginning of a reaction, you should have two reactants. It's not always. It depends on the chemical reaction that you're dealing with. Then number two, at the end of a chemical, reaction. Now, the reaction is done, and this reaction we're talking about is a successful one. Because even business, there are certain businesses that you venture into, they result into a loss, which is not a success. So the successful ones we're talking about are the ones that at the end of the reaction, we have a product, or maybe we have products. So at the end of the reaction, there may be products. Products are there for a successful one. There will be products, because that's why we are calling it success, because products are there. What else do you expect? There may be reactants or a reactant present. How truthful can it be? At the end of a chemical reaction, we are saying that there are reactants also. Let me give you this example. We are trying to make up scones. And these scones, for a single scone, we need, let me just give you an example here. For a single scone, we need one egg, we need an egg, 2 spoons of sugar. I'm just giving an example. 2 spoons of sugar. I want a spoon of salt, and maybe 3 spoons of flour. I'm just giving an example. Then, let's see, this person who's trying to make up scones has got 12 eggs. There are 12 eggs present, and then there are about 40 spoons of sugar. Salt, there are only 10 spoons of salt, as well as 45 spoons of flour. The question will be, how many scones can we make? How many scones? Is it the eggs that will determine how many scones will be made from them? Are they spoons of sugar? Should it be salt or maybe flour? So you will see that at the successful end of this baking, one of these will be done. others will remain. So at this point where I was saying that it's not always that at the end of a chemical reaction, reactants should all be done. It depends on how much of reactants that you have. It depends on the ratio of these reactants that you have. So let's guess. This is from a home-based chemistry. This is from a home-based chemistry. For a single scone, an egg, 2 spoons of sugar, 1 spoon of salt, 3 of flour. And this is what we have. Can we have someone to give us an idea how many scones we can make from that? The floor is all yours. Yes, guys. How many scones can we make? How many?
15.
15. Okay. So Muka says 15. Let's keep it that way. Muka says 15 scones can be made. Others, what are we saying? Maybe not wasting much of the time. Let's run through together. So if eggs are the ones that are determining how many scones we can make, because we need a single egg for a single scone, and because there are 12 eggs, we can only make 12 scones. If we are to use eggs as our determining reagent, because there are 12, and for a single scone, you need a single egg. So according to the information we have from eggs, we can only make 12. So Mkuka, that means even yours has gone above it. Let's see sugar. Sugar, we need 2 spoons of sugar in a single scone. And how many spoons of sugar do we have? We have 40. If you get this 2, you divide into a 40, you'll find that according to sugar, the limit we can get 20. What about salt? Salt, for a single scone, you need 1 spoon. And how many spoons do we have? 10. Meaning from salt, we can only make 10 scones. Flour, you need 3 spoons of flour for a single scone. And how many do we have? 45. So if you have to divide 3 into 45, we can make 15. And therefore, according to the information we have, we can only make 10 scones. Because by the time we are making the 10th one, salt is done. So meaning the 11th one that you're trying to make, it won't have salt. Then it won't be a successful one. So at the end of the baking, we'll still have sugar remaining, we'll still have eggs remaining, we'll still have flour remaining, but the reaction is done. This is the point I was trying to exhaust to you. At the end of the chemical reaction, some reactants may be there. It depends on how much that you have. So Mukuka, have you been reminded on how best this question could have been answered?
Yes.
Thank you. Now let's move on to something even more interesting. Something more interesting. Now, I should tell you that as you advance in your studies, you will find that there's more that is written. For now, maybe the widest assignment you ever done is just maybe a take-home test where at least you are given quite a lot of things. But as you go up, especially when you reach masters, because there you will have to do a lot of researches. And these researches are very good. That's why maybe in Zambia, we don't do much of discoveries. Most of the medicines that we have are imported. And the sad truth is that these countries where these drugs come from, they don't even have the right material for making these drugs. Some of these drugs are herbal in nature, and where do they get these ingredients? Right from our country. So look at the sad truth where you have all it takes, but you don't have the knowledge on how to get it so that you make the product. Someone comes into your yard to get whatever you have, takes it out, makes it a final product, and comes to sell it to you at a very exorbitant price. So that's why researchers are very important, because they help us to discover more. Now, what am I saying about researchers? As you present your findings, before they are certified to be true, they are called assumptions. They are called assumptions. So you assume your findings are the correct thing. So within the chemical reaction fraternity, there are some few assumptions that are there. And these assumptions are quite vital for the fact that without them, there will be no product. So this assumption is called the collision theory. So let's look at a collision theory. So there are actually only 3 assumptions that we have under collision theory. Without these assumptions, there will be no final product. Assumption number 1, it states that, let me give you a general statement. For the reaction, a chemical reaction that matter, for a chemical reaction to lead to the formation of products, for the chemical reaction to lead to the formation of products, meaning for there to be a successful chemical reaction, these 3 assumptions should be there. Number 1, they're saying that reacting particles should collide. For there to be a successful chemical reaction, the reacting particles should collide. So we are going to do a bit of a chemical reaction where we're going to use magnesium ribbon. We use magnesium ribbon and a little bit of HCl. So these are the reacting species that we have at the moment, magnesium ribbon as well as HCl. So you're saying that when these 2 are reacting, for there to be the products at the end of the day, these 2 should be put in one reaction vessel so that they collide. Otherwise, magnesium ribbon is in here, HCl is in here, you bring them closer without there being a direct collision contact. Believe you me, there will be no product. That's what we are saying. That is the first theory. That's the reason that's why even when you are cooking ishima, you use a cooking stick to do the physical mixing of mealie meal and water. We are riding on this first theory. Second one, this assumption. The second one is that the colliding particles, which are reactants, must collide in a proper orientation. Now, what that means, to do its bonding, that's where I think I can draw this part that you can understand better. Remember, lithium, Li, nuclear notation 7,3. If you had to draw this in form of electronic configuration, you're going to say lithium here. Let me just talk about the last shell, which will have an electron, a delocalized one, like that. That's lithium. Let's also look at fluorine. Fluorine, whose nuclear notation is 19, atomic number 9, the configuration will be 2,7 to make it 9. Allow me to focus on the last shell. So I'll put up 2 shells here. That's where you're going to understand the importance of this. I'll put up the first shell as shell number 1. or atom number 1, I'll put up another atom as atom number 2. Now, atom number 1, these 7 electrons, we're going to have 6 on the left-hand side, covering up, only leaving 1 lobe on the right-hand side here, where a single electron can come and fit, so that atom number 1 attains octet stability. Atom number 2 will have a different arrangement, actually the exact opposite, where we will have only a single lobe left on the left-hand side. So between the two, which one do you think is in a better position to receive this electron if it was to be lost? You will find that this atom number 2, which has a free space nearer to the site where this electron is coming from, is in a better ability to come and abstract that electron. While atom number 2, this electron will have to go around and then it finds a free space. This one leads to what is called steric hindrance. It is being hindered because the site where the electron is coming from and the site where it's supposed to be is actually on the other side. So it's highly hindered. So this leads to steric hindrance. Therefore, it might take even longer. It depends on how much energy that electron has as it moves. So that is the assumption number 3. Number 2, the reacting species must collide in a proper orientation. If this electron collides here, there are already electrons occupying that space. Due to the force of repulsion, that electron will be pushed away. The third and last assumption is that the colliding species, the colliding particles must have minimum energy. Someone might wonder, how come atoms have energy? Yes, they do have. When you buy a packet of crisps, read on the ingredient contents, the nutritional content. They also stipulate how much of energy that you are likely to get when you eat that pack. Remember again what we were looking at the other day, conservation of energy. Energy is never created nor destroyed, it's just converted from one form to the other. So when you eat that pack of crisps, when you eat those crisps, you will have energy to do work. Now that energy is coming from crisps, trapped in terms of chemical energy in the atoms that are contained in the food. So that's why I was saying that for there to be a chemical reaction, these atoms that are reacting, they should have a minimum amount of energy. And this energy is the one that is actually enabling them to react. And this energy is actually called the activation energy. So there must be some energy which must activate the chemical reaction. The good example is matches. You have a matchstick, you have a box of matches, and then you have a matchstick. This is matches, this is a box, then this is a matchstick. You get this matchstick and the box, you put them together. Without that minimum amount of energy that results from the friction, there will be no fire. So fire will only emerge, fire will only be resulted as a result of that minimum amount of energy that you apply. Should there be a lot of energy that you apply here, the box or maybe this thing is going to break. And as a result, at the end of the day, there will be no fire. So this is what we are trying to say, that the activation energy definitely must be there. Any question from the 3 assumptions? Otherwise, right from there, we'll go to factors. Then we can also perform an experiment that I have. Very simple one. Questions, guys? Do we have questions on what has been presented? Yes, Zulu, please.
What happens to the colliding particles if they have maximum energy?
If they have the maximum energy. Good. I'm giving an example of an atom. Okay, let's say two atoms are connected. Should I give you that? Let me take it to biology because maybe if I integrate subjects, it's going to make it much easier. If this particle and this particle are colliding with the maximum amount of energy, it will lead to this atom changing its shape. It will lead to this atom changing its shape and this atom changing its shape. As a result, you'll find that the arrangement, the chemical mechanism for the chemical reaction to take place will be reduced. Why? Because the proper arrangement of this atom with the actual site where the electron must go has been disturbed. As a result, you end up delaying maybe the reaction, or maybe the reaction might not even take place because the chemical orientation of these atoms has been changed. Like I talked about matches. Instead of just doing it slightly, where you even bite your jaws as if you are smashing the head of a serpent. What are you going to do? This thing is going to break. Are you going to have fire? There will be no fire. Because we just need minimum. Remember, we are just activating, starting the engine of a car. All you just need is just a little bit of ignition on the key there. The engine runs its own, produces its own, converts its own energy as the car being driven. Much of the ignition on the key, they actually are going to spoil the mechanism inside. So you just need a minimum so that the energy which is trapped within the atoms can be activated. So the key word here that is guiding us is activation, meaning there's already energy trapped inside. You just need a little bit of energy for the reaction to start, to continue now, or to start, and then it goes on and on. Have I explained in the way that you expected? Or maybe have I answered your question?
Yes.
So energy is already there. Or you look at petrol. Petrol can burn, but without fire, it won't. Without heat, it will not produce heat. Or you just need just a little bit of heat on petrol, and then the burning goes on and on, actually in a very, very uncontrollable manner. But why did it start on its own? It needed a little bit of energy so that that energy trapped within itself is activated. Thank you so much. Second question before we move on. Second question before we move on to the last part of the presentation, which is going to have a little bit of a demonstration. You know how much I love practicals. Yes. Who is that? Chiza. Thank you so much. Chiza, please.
Can you please define steric hindrance again?
Steric hindrance. It's not there in your syllabus. I just borrowed it from advanced organic chemistry so that maybe I can just provide a better understanding. But I wouldn't even advise for you to have it in your notes.
Okay.
There are certain concepts that from the science perspective are hard to explain. But when you bring in maybe one or two borrowed words from advanced levels of learning, they provide a basis for one to have a clear picture. Like, because if I just say it in a proper orientation and I end there, how best were you going to explain? How best were you going to learn? Or maybe how best was I supposed to explain so that you understand it? So I borrowed in an advanced word, which when explained at maybe a lower level, then it provides a better link for you to understand. So I wouldn't even put it up on the notes. If I wanted, I could, because no, it's a little bit of advanced. I'm not avoiding your question, but I'm just trying to make sure that we stick to what is best for us. Maybe on your own, I can explain to you, but not from here. Thank you so much. Next question, maybe one or two, then we can move on. Okay. Now, I was saying, some reactions are very fast. Burning. This reaction is very fast, especially if you're dealing with the right fuel. Burning is one of very rapid, one of many rapid reactions that we have actually. And yet we also have some reactions that are very slow. Ripening of fruits. At the backside of your yard, start monitoring this fruit that is coming from the inside of the flower. To take a lot of time, for it to get to a point where it's ready for consumption. It will have taken a lot of time. Yeah. So we have to understand that factors factors that affect the rate of air chemical reaction. Yeah, so there are quite a lot of factors, quite a lot. But in the interest of time, I'll just look at one, and maybe just within 5 minutes, we look at how this factor can affect the mode of operation, or how fast the reaction or how slow the reaction is, and then we end here. We reserve the rest for some time later. So we have to note that, some reactions are fast and others are slow. In fact, very slow. Very slow. So meaning to these ones that are very slow, I'm sure we can do something to them so that they are speeded up. And to those that are very fast, there should be something that we can do to them so that they take longer for the reaction to be done. That's the first point. Second point is that the reaction that takes less amount of time. The reaction that takes less amount of time, that's one that is very fast. And the reaction that takes longer to be completed, that reaction is very slow. So the factors that we are going to look at are quite a lot, but I'll just give one which we will discuss within the limited amount of time that I'm remaining. And this factor is called concentration. What is concentration from a stoichiometry point of view? Concentration, we're talking about the amount of solid that are dissolved per liter of a solvent. So we have a solution. Let's say we have deionized water. We get maybe just 500 mils of deionized water, which is a solvent. And should we weigh magnesium ribbon, which is a solid, the amount of this magnesium ribbon that's going to sit in that solvent is going to determine how concentrated that solution will be. So that's why I'm saying concentration is the amount of solute in a solvent. Now, if this first system that we have not enough solute in the solvent, meaning particles are quite far apart from each other. Then we also have another system. In this system, the solids are quite a lot, meaning the spaces in between them are quite short. So between the two, where do you think the reaction will take place faster if an external particle was introduced? Definitely, it will be in system number 2, because there are quite a number of viscous particles that can easily attack whatever goes in there. So we can say that this one is highly concentrated and this one is not as concentrated as that one is. So how does concentration affect the rate of the chemical reaction? So we are saying that concentration is the amount of solute. These are measured in moles. The amount of solute dissolved in a unit volume of a solid. Now, how does it affect? You are saying that when the concentration is high, the higher the concentration of reactive species in form of a solution, the faster the rate of a chemical reaction. Yes, now this point here actually very, very important, especially for those that would want to venture into the fields of environmental monitoring, toxicology. The concentration is quite important here in the fields of toxicology, as well as in the fields of physical chemistry. Yeah, physical chemistry concentration is also very important because from here we develop the CD50. Yeah. It's very, very concentration is a very important concept in the fields of science. We're saying that when the number of moles in a solute is higher than the other, we expect the rate of a chemical reaction to be faster. And if it is very fast, we expect this reaction to take less amount of time. So right on this, as we conclude, I have something for you. And this something I have, like I said, we have HCl, which is at, they didn't put the normality, they didn't put the concentration. Yeah, so I don't know how concentrated it is. We need to do titration so that we can determine the concentration. Should be highly concentrated. We also have deionized, which is commonly known as distilled water. We have our measuring cylinders. One will be used for the acid, the other one will be used for water. We also have, it's a virtual experiment, unfortunately. We also have, for the sake of accuracy and precision, we're going to use unique or individual water bottles. We have the vessel for a reaction, we're going to use a beaker. Precaution number 1, put on protective goggles, protect your eyes, because tomorrow you need to see where Amanda is. Precaution number 2, we're handling acids, so it's very important that we protect our hands so that tomorrow we will greet each other in a very good way. So we have the gloves. Okay? So how can we tell that the reaction is very fast? We will consider the time that each reaction takes. So precaution number one, put on your protective goggles, protect your eyes. Number two, you have to put on your gloves because you are dealing with acids with the unknown concentration. And then number three, you make sure that this reaction is done in an open area. The reason is when you react magnesium as well as HCl, that's a single displacement reaction, meaning we'll have only two products, a binary compound, magnesium chloride, as well as diatomic product, which is hydrogen. And we understand that hydrogen, when it is dry, it's odorless, but because it's coming from a solution, so it's going to contain a little bit of the acid. So this hydrogen is going to have a little bit of a pungent smell. So let's begin. What do? We are going to first have an acid in here. This acid will just measure 50 mils of the acid. We get magnesium ribbon. We see how long it's going to take for this magnesium. It's not magnesium ribbon, it's magnesium metal. We see how long it will take for this magnesium metal to dissolve. Then thereafter, I wish I used magnesium ribbon. I'll just do 3. Then thereafter, we are going to add a little bit of water because when we add water, we are reducing the concentration. We are diluting. So because the dilution reduces the concentration, the second reaction, you expect it to take longer. Let's go. Yeah, so I think, guys, we'll do this tomorrow. In the interest of time, we can do it tomorrow. How many want to do it now? How many want to do it now? Mukuka. Okay, let's do this. The time for physics, we are going to continue with this experiment. The time for physics, we are going to continue with this experiment so that I don't interrupt the time for mathematics. I know you guys are anxious you are about this experiment, but I'll leave everything here. Time for physics. Thank you so much. See you later.